Hello, thanks for clicking on this video. My name is Marius Oltean, and I'd like to tell you a little bit about recent work I have been doing on the topic of the equations of motion of extreme mass ratio in spirals. This is work in collaboration with Carlos Sopuerta in Barcelona, Alessandro Spallicci in Orleans, Richard Epp and Robert Mann in Waterloo. I'll begin with a brief introduction and motivation of the topic, following which I'll divide the main bulk of this talk into two parts, each to give you a bit of an idea of recent projects, two projects or directions that we have been working on in this area. One involves conservation law formulation of the gravitational self force, and the other a numerical method for computing the self force that we refer to as the particle without particle method. At the end, I will offer some conclusions. So the main motivation for the problems we have been considering come from trying to better understand and model systems called extreme mass ratio in spirals, which are expected to be among the main sources of LISA. They are compact binary systems where one of the objects is much more massive than the other. And here you have a picture of what some of the orbits as well as waveforms of these systems are expected to look like. The expectation is that LISA will see anywhere from 1 to hundreds or 1,000 of these systems per year, with the number of cycles in the final year before the plunge being like the inverse mass ratio, so thousands, tens of thousands. This makes such systems ideal experiments in strong gravity. Among other things, they will permit us to measure the mass and the spin of the black hole to very high accuracy, to test how well the Kerr solution describes black holes, and to test general relativity itself. The main problem, however, arises from the fact that the signals from these EMRIs are expected to be much weaker than the instrumental noise of LISA, thus requiring very accurate modeling for the data analysis. This problem has been under development for the past more than 20 years, with much progress having been achieved, but many challenges remain. Essentially, one has to treat this problem perturbatively, and to compute the perturbative correction to the motion of the small object away from geodesic around the large object. Up to now, most approaches have described the small object as a delta function and have attempted to compute this correction at the location of the moving body, thus requiring many methods to deal with the singularities introduced in this way into the problem. As an alternative to this, and motivated by various other reasons also, we have been considering a formulation, and we have developed a formulation of this problem with the use of conservation laws. So instead of computing the correction to the motion at the location of the delta function, instead to describe the correction as a change in the momentum due to a flux through the boundary of the extended system. Conservation law ideas have in fact proven useful throughout history in the analysis of the self-force problem. Already in the 30s, Dirac developed a formulation of the electromagnetic self-force on the basis of the conservation of the matter stress energy momentum tensor, which I write as capital T. So for the evolution of any finite system through spacetime, one may have a flux of matter passing through the boundary, and then the change in the momentum of this system can be expressed as a surface integral involving this tensor. This idea was then extended to non-dynamically curved spacetime by DeWitt and Brehme in the 60s, and more recently, generalized killing fields have been used for the electromagnetic and scalar self-forces. Yet, to our knowledge, prior to our work, there had been no formulation of the gravitational self-force following a general, and by this we mean quasi-local, which I will explain what it means, conservation law approach. Indeed, one of the first formulations of the gravitational self-force by Mino Sasaki Tanaka had in fact made use of conservation principles, yet treating gravitational energy momentum just like matter. This happens to work in a lot of situations in practice, not only in the self-force problem, but in general relativity generally, yet fundamentally does not make sense in principle. And this has to do with the general definition and notion of gravitational energy momentum. So let's consider the question how we would define gravitational energy momentum inside of a finite spatial volume V that we can consider evolving through spacetime. Pre-relativistically, the answer given to this question would be something like, there exists a local volume density, which when integrated over the volume gives the total energy momentum inside. And this is known as a local notion of energy momentum. With the advent of relativity, however, it was understood, and arguments as simple as ones that can come from the equivalence principle can be given towards this, that gravitational energy momentum is not localizable. There cannot be a local volume density of gravitational energy momentum. So instead of this idea, one idea that does seem to work and has proven useful in practice in many applications is to replace the notion of a local volume density with that of a boundary density, which when integrated over the boundary gives the total energy momentum inside. This is known as a quasi-local notion of energy momentum. And so just as one gets the local volume densities for matter from the stress energy tensor of matter, one gets these boundary densities from a quasi-local stress energy momentum tensor for both matter and gravity defined on the surface. The definition we take for this tensor up to a factor is that of the canonical momentum of the boundary. This is known as the Brown-York tensor. It was introduced and motivated by the authors in the 1990s, and we label it here as tau to distinguish it from the usual T, denoting the usual stress tensor, local stress tensor of matter alone. Conservation laws for both matter and gravity, for energy momentum and angular momentum, have been developed on the basis of this Brown-York tensor with the use of an additional construction called quasi-local frames. So essentially the idea is that one needs additional structure on this world to boundary in order to specify the directions of this Brown-York tensor, energy momentum and angular momentum, that one is considering for the conservation laws. In particular, what is needed is a congruence on the boundary constituting the boundary. A two-parameter family of time-like world lines, the union of which is precisely the world-to boundary of the system. We have taken then these conservation laws and applied them to a one-parameter family of perturbed spacetimes, which is depicted here visually, and from which we have obtained in this way the self-force, the gravitational self-force effect. So we have only considered a general one-parameter family of spacetimes. In the EMRI problem, the background is Schwarzschild or curve, but we have done it for a general background too. Considering the small system moving in the perturbed spacetime as depicted here, and having a quasi-local frame on the boundary of the system. We then mapped the conservation laws from the perturbed spacetime to the background and considered what these conservation laws look like in the background. And we have found that assuming there is no matter flux, which we can take into account if desired also, but without the matter flux, then the change in the linear momentum of the system in a direction determined by a vector phi, which is described in more detail in our paper, is given by a flux through the world-to boundary between the initial and the final time. Specifically, it's this Brown-York tensor contracted with the gradient of this vector, pulled back to the background spacetime. Expanding this to linear order in the perturbative parameter, the perturbed gradient term of this expression is dominated at leading order in the areal radius, which is 0th order of the system, by what we refer to as an extended gravitational self-force, which we denote by script F. So the change in momentum has this form. It's an integral over the boundary of this extended self-force contracted with the direction vector. This extended self-force for vector is a sum of two pieces. The first is the known so-called bare gravitational self-force. That is to say, the self-force, the gravitational self-force known up to now, evaluated with the metric perturbations directly on the boundary, so no regularization needed. And the other piece is a novel term that we have found, which we refer to as the self-pressure. Respectively, they arise schematically from an energy times perturbed acceleration plus pressure times perturbed gradient terms. In particular, this energy and pressure is that of the gravitational vacuum. We have, moreover, related our results to a specific self-force analysis, in particular that of Gralla and Wald, and have related our results to the equation of motion of Gralla in what he referred to as an angle average form. That is, instead of evaluating it at the location of the object, to average over the angles around it. Let me turn now to the second topic, which is the numerical method we have been using for actually solving the equations for computing the self-force, the equations of motion, which we call the particle without particle method. And to give you first the basic idea, which comes up in situations in gravitational physics where we need to solve for the self-force, and in many other areas of applied mathematics as well. So we have partial differential equations for a function that I call small u that have this form. We have a partial linear differential operator on the left side acting on the function of interest, and the source on the right side is distributional on the solution, on the problem space. In the gravitational self-force problem, for instance, common examples of this are in a Schwarzschild-Droste background, for instance, the scalar self-force has a source which is a function times a delta. In the gravitational case, one adds a delta prime to the source. And in Kerr, it's similar, just in the gravitational case, it gets more complicated. One has a delta double prime. Let's take the scalar self-force case for simplicity and see how this method works. Consider in the time radial space, the object moving around the central black hole and moving between some apocenter and pericenter, with the equation to be solved schematically being the one written here in the box. The idea of this particle without particle method, which was initially developed by Carlos Sopuerta and his previous student, Priscila Canizares, is to divide or to split up the solution into two parts, or as many as are required, but in this case, two is enough, of Heaviside functions supported to the left and to the right of the particle. So one inserts this decomposition into the original equation, and the original equation becomes transformed into homogeneous problems on the solution space minus the support of the source, supplemented with, so to the left one will have a homogeneous problem as well as to the right, and supplemented with jump conditions, effectively boundary conditions, on the solution or derivatives of the solution across the source of the distribution. So previously, this had been applied with success to computing the scalar self-force in the time domain. More recently, we extended this method and showed that it will yield solutions to any partial differential equation of the form written here in the box. So the source can be any linear combination of delta functions or derivatives of delta functions at an arbitrary number of particles in one dimension. We have, moreover, applied this to solving some other problems in diverse other areas of applied mathematics where similar partial differential equations are involved. Now we have been working on on applying this method to computing the scalar self-force in the frequency domain, which as opposed to the time domain should be computationally faster, and also permits an extension of this to Kerr, specifically by using pseudospectral collocation grids in order to solve the differential equations. And we have obtained consistent results for circular orbits and are working on the eccentric orbits. Let me offer some conclusions. So we have developed a conservation law formulation of the gravitational self-force, which is geometrical. It is by construction free of divergences. It does not fix the perturbative gauge a priori, unlike other treatments that have been used up to now for the gravitational self-force. And moreover, it also often offers an explanation for the origin of the gravitational self-force as an interaction between the vacuum energy and pressure and the metric perturbations. Further from here, we would like to further study our formulation and compare it more with other formulations of the gravitational self-force, also to develop some numerical implementation of this formulation. Also, we can go to higher orders either in the perturbative parameter, so the second order self force, for instance, or in the areal radius considered for the problem, and also study the electromagnetics self force problem within this formulation. It would be very, very interesting. We have also developed a numerical method for computing the self force called the particle without particle method, and using it for the computation of the scalar self force in the frequency domain. So far, we have circular orbits, and we are working on developing the eccentric orbits. We encourage any questions or comments that you have, please send to any of us, and I thank you very much for your attention.